Welcome. In this video, we're going to complete proofs about quadrilaterals. Now, we're going to focus in these upcoming videos on proofs about parallelograms. Now, parallelograms are quadrilaterals that have two pairs of opposite sides parallel. There are other things that are true about parallelograms, and we'll go over those before we begin the proofs. Parallelograms are just average parallelograms, but then there are special parallelograms that, besides all of the features of a parallelogram, have some unique properties as well. Right? So there are two types of parallelograms I want to talk about right now are rectangles and rhombi. So rectangles are parallelograms, which means they have all the features of a parallelogram. Both pairs of opposite sides parallel, both pairs of opposite sides congruent, both pairs of opposite angles congruent, consecutive angles supplementary, the diagonals bisect each other, but they also have four congruent angles, four right angles. So a rectangle is a parallelogram with right angles. Because it has four congruent right angles, it also has congruent diagonals. Right? And we can use that to prove that a figure is a rectangle. Rhombi is a parallelogram. So again, all the features of a parallelogram, but this is a parallelogram that has four congruent sides. So not only are the opposite sides congruent, all of the sides are congruent. Because it has four congruent sides, it has diagonals that are perpendicular. In other words, they meet at right angles. And those diagonals bisect the opposite angles. So these are all congruent as well. Now, when we work on coordinate proofs, we really won't be working at all on angles. The only type of angle that will ever appear in a coordinate proof is right angles. We can prove that an angle is a right angle by showing that the lines that created that angle are perpendicular. But other than that, it's very hard to do any kind of proofs on coordinate proofs with angles. So we won't be working at all with angles except to show something is a right angle. And then we have the square. Now, the square is a type of parallelogram, but it's also a type of rectangle and a type of rhombus. So everything that's true about the rectangle with the four congruent right angles and the congruent, I actually didn't show the congruent diagonals. I should have showed the congruent diagonals. The congruent diagonals are true. And everything about a rhombus is true for a square. So it has four congruent sides as well. And because it has four congruent sides, the diagonals are perpendicular and they bisect the angles. And I can't show any of that on that little tiny square, so I'll just tell you that. Another group of quadrilaterals is the trapezoid. Now, the trapezoid only has one pair of opposite sides parallel. Right? And those are called bases. The bases are the ones that are parallel. Right? So it just has one pair. Now, there are two special types of trapezoid. So there's just regular, any figure, any quadrilateral that's got one pair of parallel sides is a trapezoid. If it also has the other two sides that aren't parallel are congruent. The two sides that aren't the parallel sides are called legs. Right? The parallel sides are called bases. The other two are called legs. If those legs are congruent, then we call it an isosceles trapezoid. Now, isosceles trapezoid is a trapezoid with equal legs. It also has congruent diagonals. So these diagonals here are congruent. That's why it's not enough to prove that a quadrilateral has one pair of parallel sides and congruent diagonals to call it a rectangle, because an isosceles trapezoid also has one pair of parallel sides and congruent diagonals. So if you want to prove a quadrilateral is a rectangle, you got to show it's got two pairs of parallel sides and congruent diagonals. Or any other, you have to prove anything that's true about the parallelogram is true before you can say something is a rectangle. Right? And then another type of trapezoid is the right trapezoid. So it has, again, it has the one pair of parallel sides, and it has a pair, has two right angles. Right? So two right angles and one pair of parallel sides. And those right angles are consecutive. They're one after the other. Right? That's why you can't just show a quadrilateral has a right angle and then call it a rectangle. Right? Because a right trapezoid has a right angle. It has two right angles. Right? And it is not a rectangle. So whenever we're proving that a figure is a rectangle, we're always going to show it's a parallelogram first. Right, so, and then the final grouping of quadrilateral is the kite. Now, kite has two pairs of consecutive congruent sides. Now, because it has those two pairs of consecutive congruent sides, it does have perpendicular diagonals, and then the diagonals also bisect the angles. So now, that's why it's not enough to prove that a figure has perpendicular diagonals and call it a rhombus, right? Because the kite has perpendicular diagonals. So whenever we're proving a figure is a rectangle or a rhombus, we're going to prove it's a parallelogram first. Whenever we're trying to prove a figure is a square, we're going to prove it's a rectangle and a rhombus, and that will show it's a square. Right? We're really not going to work with kite proofs and trapezoid proofs. We're going to focus on parallelogram proofs. And we'll also look at some circle proofs and some triangle proofs, but mostly parallelogram and special parallelogram proofs. And we're going to do one proof now. Now, before we do that proof, want to review the features of a parallelogram. So a parallelogram is a quadrilateral with both pairs of opposite sides parallel. And here we have a parallelogram. DC is parallel to AB. DA is parallel to CB. It has two pairs of parallel sides. Okay. Now, how would we go about showing that we have a quadrilateral with both pairs of opposite sides parallel? Well, we would use the slope formula, right? The slope formula gives us the slope, and we can use that to show we have parallel sides, right? Just like we did in the previous Nearpod lesson, we proved two lines were parallel. If we're trying to prove a figure is a parallelogram, one way we can do that is to prove both pairs of opposite sides are parallel, and we will do a proof like that. In addition, the opposite sides of a parallelogram are congruent. So we could use the distance formula and prove both pairs of opposite sides are congruent. And as a reminder, the distance formula, we take the square root of the difference of the x-coordinate squared plus the difference of the y-coordinate squared. And that gives us the distance from one point to another point. All right? Now, so we can use slope, we can use distance, or we could use slope and distance together. So we have a third way to prove that a figure is a parallelogram, and that is to show one pair of opposite sides is both congruent and parallel. Right? So that works out really nicely too, and you might have horizontal, if like one pair of sides were horizontal, right? It might be nice to use that one because it's pretty easy to figure out the distance of a horizontal line and the slope of a horizontal line. Right? So we can show both pairs of opposite sides parallel, and then we'd use the slope formula. We can show both pairs of opposite sides congruent, and we use the distance formula. Or we can show one pair of opposite sides is parallel and congruent, and we would use both formulas, but just one time. A fourth way that we could show a figure is a parallelogram is to show that the diagonals are bisected. So if you remember, the diagonals of a parallelogram bisect each other, which means they divide each other into two congruent parts. Now, how do you go about proving that the diagonals bisect each other? Well, you show that they have the same midpoint. Right? So if, let's call this one diagonal I don't want to use the same letters, A, B, C, D, E. Let's call that diagonal E, and let's call this diagonal F. All right. So if diagonal E has this value as a midpoint, and diagonal F has this value as a midpoint, then they have the same midpoint. And if they have the same midpoint, the diagonals are bisected. So now to show this was true, we would use the midpoint formula and show that both diagonals, diagonal E, or I could have called it diagonal DB, and diagonal F, or I could have called it line segment AC, have the exact same midpoint. We would be able to show that this was a parallelogram. And that's actually what we're going to do right now. I actually think it's one of the easiest ones. Right? Now, as a reminder, right, these are our steps when we're working, when we're completing a coordinate proof. Right? This information is already in your notes. So first, we're going to draw and label the diagram if it's not already given to us. In the next example, I already have the diagram drawn for me. You'll just have to draw it. No big deal. We're going to write down the geometric conditions that are required. In other words, what do you want to show? Third, you're going to state the formulas that are used. They become your reasons when we do the proof. Step number 4, you're going to show all your work, right? Whether are you using the slope formula, and then show the slope. The slope formula, right? If you're using the distance formula, show the distance formula. If you're using midpoint formula, show how you got the midpoint, right? So we're going to show all our work. That's step 4. And then step 5, we're going to write a proof. We're going to either do a paragraph proof or a 2-column proof. I left it up to you, I believe, in the notes, in the homework. I'm going to switch back and forth between doing a paragraph proof and a 2-column proof. The next proof I do is going to be a 2-column proof. All right, so we have 4 ways, and so we're going to eventually do 4 proofs for proving a figure is a parallelogram. Right? And it tells you on the homework which one to use, but all of these work. Right? So method 1, we can show the diagonals bisect each other by showing the midpoints of the diagonals are the same. And by the way, this is in your notes. If the writing's not there, it might be. Then add the writing. If it's already there, well, then you don't have to add the writing, now do you? Right? And so to show diagonals bisect each other, we're going to use the midpoint formula. It really is a very easy formula. Method 2, show both pairs of opposite sides are parallel by showing they have equal slopes. We'll use the slope formula. Method 3, show both pairs of opposite sides are equal by using the distance formula. And then method 4, show one pair of opposite sides is both parallel and equal. You'll use the distance formula and the slope formula. Right? Notice we don't work with angles because it's really impossible to prove anything about angles other than right angles on the coordinate plane. And here's our proof. All right, so the first thing you're going to do is you're going to graph this figure. And we have point L located at -2, -2, 3. So graph the point, -2, 3. We have M located at 4, 3. All right, so here's 4, 3. We have point N located at 2, -2. We have point O located at 4, -2. Excuse me, -4, -2. And then you're going to connect. When you connect points, right, so these normally wouldn't be here, right? I added those in. So this is what you have. I'll move those away, all right, and then I'll just move them on there. Just trying to save time because we know sometimes a line tool likes to be finicky. All right, so this is what you see. When you connect, you go in order. All right, so you don't go from L to N. No, you go from L to M because that's how it's listed. Then you connect from M to N. Then you connect from N to O. Then you connect from O back to L again. Now, if you are completing a proof about diagonals, go ahead and connect the diagonals. So they go across and they are non-consecutive points. Right? So L and N are non-consecutive. They're not one after the other. And O and M are non-consecutive points. So those are our diagonals. Right? So that right there, that is step 1. Okay? So the first thing we did is we graphed it. Right? So ignore this. This just tells you what problem it is. Step number 2, we are going to what do we want to show? Right? So by the way, all the parts I write up here, you write too, and this is what your homework will look like. Right? And if a problem is on the homework, then I will tell you this problem is on the homework, so you can use it as a model. Right? So step number 2, we show. What do we want to show? It says it right there. Right? And your homework will say it as well. Right? We want to show that the diagonals bisect each other. How do we show that? We show that by showing that the midpoints of the diagonal are the same. All right, now our next step, maybe I'll change colors each time, is the formula. Well, if we want to show the midpoints are the same, we must be using the midpoint formula. The midpoint formula is the difference in the x coordinates divided by 2. That gives you the x value of the midpoint. And then the difference of the y in the y values divided by 2 gives you the y coordinate of the midpoint. Midpoint is in the middle, so we're going to average the x coordinates and we're going to average the y coordinates, and that gives us our midpoint. Step number 4 is our work. All right, so we want to find what point that is right there. All right, we want to find the midpoint of LN and we want to find the midpoint of OM. Right? If that midpoint is exactly the same, then the diagonals bisect each other. All right, so our work, I'm going to write the coordinates right here just to make that easy on us, because that's all, we're just using these points, right? So we're going to find the midpoint of LN first, right? Because that's the diagonal. Right? So we take the difference in the x coordinates, -2 plus 2, divided by 2. And this is for LN. I probably should write that. And I'm just going to put a little m here to stand for midpoint. All right? So, and you can use whatever letter you like. But m for midpoint makes sense, right? So -2 plus 2 divided by 2. And then the difference in the y coordinates divided by 2, 3 plus -2 divided by 2. All right? So -2 plus 2 is 0. 0 divided by anything is 0. -3 plus a negative, 3 plus -2 is 1, and that's 1/2. All right, let's do the same thing, but find the midpoint for OM, and O is -4, -2, and M is 4, 3. All right, so now we have OM, and we're going to add the x's together, -4 plus 4 divided by 2. Add the y's, -2 plus 3 divided by 2. All right, -4 plus 4, that's 0. And -2 plus 3, that's 1, and it'd be 1 divided by 2, or 1/2. So that's all our work, right? So this is not all that difficult. All right, and now let's do our proof. We're going to do a 2-column proof. We have statements. So this is step 5, and it's our last step. We have our statements, and for every statement, we have a reason. This particular proof has 4 steps. Step number 1, you got to start with something. What did we start with? We started with those points there, L, M, N, O. We started with that figure. Why did we start with that figure? Well, it was given to us. Right? We didn't make it up. We were given that. Step number 2, we found the midpoint of LM. And that was 0, 1/2. And we found the midpoint of OM. Oh, that's an N. That's a terrible looking N, by the way. This is LN, and this is OM. And that was also 0, 1/2. How did we find that midpoint? We used the midpoint formula. You don't have to be all fancy and say a lot of stuff. You don't have to say, I used the midpoint formula. Just say midpoint formula. That's where those values came from. That is a little farther than I wanted to scroll up. Let me just move that down just a little bit. I just need a little bit more space. I still want you to be able to see the whole proof. There we go. Huh? I need a little bit more than that, Mr. Board. There we go. All right, step number 3. The diagonals are bisected. That's what we're trying to prove. Says it right up in there. Prove that the quadrilateral has, no, I can't see it anymore. Let me scroll back up a little. We want to show the diagonals bisect each other, right? We've shown the diagonals bisect each other. How do we know? Because the midpoints of the diagonals are the same. All right, so our reason for step number 3, diagonals have the same midpoint. If you remember from the parallelogram lesson, all those parallelogram lessons we did, that whole unit, or just the fact that I said it in the previous slide, if the diagonals of a quadrilateral both bisect each other, the figure is a parallelogram. So LMNO is a parallelogram. How do we know? It's a quad whose diagonals both bisect each other. And that's it. All right, we have proved this is a parallelogram. That's all there is to it. These are not extraordinarily long proofs, right? We start with our given. Then we go to our work. Your reason is always going to be, is it slope formula, is it midpoint formula, is it distance formula? All depends on what the proof is. Here, we proved that the diagonals have the same midpoint, so we use the midpoint formula. Because they have the same midpoint, these diagonals bisect one another. That makes it a parallelogram, because a quadrilateral whose diagonals both bisect each other is a parallelogram. All right, and that's the end of this video. Thanks for watching. Bye for now.